Okay, everyone. Good afternoon. We're going to take a look at, in this video session, how to analyze circuit puzzles 6, 7, and 8. These are more complex circuit puzzles that have a combination of series and parallel together. I'm going to remind you, I'm going to turn on my comment tools because it's helpful to be able to annotate different things along the way. One of the things that I do want to remind you, the most important step of starting this thing is to trace the current through the circuit. Okay, make sure you do that. Now, I took the liberty of doing that for circuit puzzles 6, 7, and 8 so that I could color code it for you. You can see the total amount of current is colored in black. And that total current has split up into current going across the middle pathway that I colored in blue, and current across the outer pathway, which is colored in gray. The blue current plus the gray current has to add up to the total black current going across the battery. So what we're going to do is we're going to use a combination of Ohm's law concepts. Okay, remember Ohm's law, V equals I times R, I equals V over R, or R equals V over I. And we're going to use series and parallel rules in order to discuss the idea of current and voltage, right, being either the same or summed in a series or parallel circuit. So we have to know what we're looking at as far as a series or parallel circuit in order to know how to analyze it. That's why this becomes the most important step to start the problem. The first thing I would do to start any circuit puzzles, I would always look to see if I have two of these three variables, voltage, current, and resistance, and see if I can use an easy Ohm's law calculation to start. For instance, you guys see that I have total voltage and total current. So I could do total resistance by going voltage divided by current, or 10 total amps, or 10 total ohms of electrical resistance. But beyond that, there's no other calculation that I can do at this point other than start my analysis, okay? So that's where we're going to begin circuit puzzle number 6. So here's where we're going to start. I'm going to take a look at the current side of things first because I see the total amount of current is given in the problem as 5 amps, and again, colored in black. I see that current split up. Now, 2 amps is recorded across resistor 1. 3 amps is recorded across resistor 4. Remember, 2 plus 3 equals 5, right? However, how much current is going across R2 and R3? Well, let's take a look at this. Current in a series circuit is the same. So if there's 2 amps of current going across R1, R2 also has 2 amps of current because they are on the same series pathway. Similarly, R4 has 3 amps of current going across it, so R3 must also have 3 amps of current going across it because these two are on the same series pathway. So R2 is 2 amps, R3 is 3 amps. And the 2 amps across this pathway plus the 3 amps across this pathway adds up to the 5 total amps of current. So we used the idea of series current being the same to start this puzzle. Now we still don't have much to go on because we could use Ohm's law to figure out resistor 2 and resistor 3 since we do know those. So 25 volts divided by 2 amps is 12.5 ohms, and 10 volts divided by 3 amps is 3 1/3 ohms. So we could do that. It's easy to kind of do the calculations as you go because they're very easy calculations to do. But now how do we figure out these missing voltages? Okay, so here's how we can try this. The battery itself is recorded as 50 volts. What that means, ladies and gentlemen, is the positive side of the battery. So this is the positive side right here, and this is the negative side right here. Well, the positive side of the battery is the recorded 50 volts. The negative side is actually 0. That gives you a potential difference of 50 minus 0, which is 50, across the battery. Okay. Now, all of this corner here, and this corner here of the circuit, all 3 of these corners are connected to the positive side of the battery, meaning they're connected to a region of high potential. So they are also going to have a potential of 50 volts. So I'm going to fill that out. 50, 50, and 50. Okay, and similarly, this corner, and this corner are all connected to the negative side of the battery or an area of region of low potential. So this has a potential of 0 volts, 0 volts, and 0 volts. So now if we look at this, parallel voltage is the same. What's the voltage across this whole first pathway here? 50 minus 0 is 50. That's the 50-volt battery. What is the potential difference across the whole blue pathway? 50 minus 0 is 50. Now, here's where the puzzle comes in. If the whole pathway has a potential difference of 50 volts and 25 volts is already here across R2, that must mean that R1 is also going to be 25 volts. Why? Voltage in series is summed. 25 plus 25 adds up to the 50 volts. But then what about R4? Well, we know R3 has 10 volts across it, and the whole pathway that includes 3 and 4 is supposed to have 50 minus 0 or 50 volts. So if 10 volts is going across R3, that means there must be 40 volts across R4. Why? 40 plus 10 has to add up to the 50 volts across the whole pathway. Okay, so that concludes the puzzle portion of it. The rest of it is pretty easy calculation. So what we'll do is we'll go Ohm's law for resistance, resistor 1, 25 divided by 2 is 12 and a half, and resistor 4, 40 divided by 3 is 13 and a third. Now to get your powers, we're going to multiply current times voltage for each one. So 5 times 50 is 250. 2 times 25 is 50 watts. 2 times 25 is 50 watts. 3 times 30 is, or 3 times 10, excuse me, is 30 watts. And 3 times 40 is 120 watts. Now here's what you have to remember to do in order to know that you're doing the puzzle correctly. Take your individual powers for resistor 1, 2, 3, and 4. Add them up. Now if we add up those individual powers, 50 plus 50 plus 30 plus 120, indeed all 4 of these individual powers do add up to the total power of 250 watts that we got from multiplying 5 times 50. If your individual powers add up to the correct total power that you get from multiplying current times voltage, then you know you are doing the problem correctly. Okay, that concludes question number 6. Let's move on to number 7. In puzzle number 7, you can see we have some unknown voltage, but I'm going to put the positive side here and the negative side here just to remind us. Okay, and we trace the current through the circuit. It's already been done for you, but we're going to follow what's already been done. The black current is the total current, and the black current is going to split up here, and it's going to split up here into the blue and the gray. So the blue current goes across the top, R3, the gray current goes across the 4, and it adds up to the total current that you were starting with here. That same total current splits up again into dark green and light green, okay, across R1 and R2. The two greens come back together to form the total current back to the battery again. Now you'll notice, guys, we don't have a single current given in this problem. We do have a couple things we can do, okay? A couple ways we can start. One of the things we can do is we know the voltage here and the resistance here. We can calculate the current using Ohm's law. Current equals voltage divided by resistance. So if I go 12 volts divided by 2 ohms, I get 6 amps across resistor 1. So I'm going to annotate that. So 6 amps going across R1. Then I can go 24 volts divided by 4 ohms, and I have also 6 amps going across R3 down here. So annotate that, 6 amps going across R3. Okay, now here's the thing. I don't have enough information to go off of to figure out what R2 and R4 current is yet. I know that 6 amps plus some other current is going to add up to my total current. So my total current must be greater than 6 amps. I just don't know what it is yet. So now is where I need to go to my voltage side of things to figure out the rest of the puzzle. Because parallel voltage is the same. Okay, so what that means is from here to here, there's going to be a voltage drop across this combination of resistors, and that voltage drop is going to be exactly the same. So since I know that R3 has a voltage drop of 24, then that means R4 must have the exact same voltage drop of 24 volts, because parallel voltage is the same. Similarly, R1, which for some reason I didn't label, let me go and label that now, R1 has 12 volt potential drop across R1. Since R2 is in parallel with R1, the voltage drop across R2 is also 12 volts. Remember, voltage in parallel is the same. Okay, so now we filled out a lot more. If I take 12 volts divided by 4 ohms, I get 3 amps of current. 3 amps of current going across this pathway. And if I take 24 volts divided by 8 ohms, I get also 3 amps of current going across this pathway, the gray pathway down here. Now it's starting to make sense. The black current split up into the blue and the gray. Well, the blue is the 6, the 3 amps is the gray. 6 amps plus 3 amps is 9 total amps. You had 9 total amps going into the break, into the parallel split. That must mean you have 9 total amps coming out of the split. Same over here, you have 9 total amps of current going into the dark green and light green split. You have 9 total amps coming out of it, which means you have 9 total amps going back to the battery, and you had 9 total amps coming from the battery. Therefore, the total battery current must be 9 amps. Okay, now what about your voltage? All right, we know the total voltage is going to drop all the way to 0. Okay, I'm going to erase this. Okay, there we go. All right, we know that there is 0 volts of potential on the negative side of the battery. We don't know the voltage on the positive side, but we do know that the voltage will drop continuously until we get to 0 all the time. That means the voltage drop of this plus the voltage drop of this has to add up to the voltage drop that you started, the total voltage of the battery that you started with, because it all has to subtract to get to 0. Okay, so here's how we can figure this out. And I'm going to draw this for you. This whole chunk, this parallel chunk right here, R3 and R4, has a voltage drop of 24 volts. It doesn't matter if I had a million resistors in parallel. From this point here to this point here, there is a potential drop of 24 volts. Similarly, from here all the way to here, there is a potential drop of 12 volts. Now, if the voltage subtracted from the total 24 and then another 12 to get back down to 0, that means the total that you started with must have been 36 volts. Okay, so if I start with 36 volts and I do a voltage drop across this first split pathway of 24, I'm down to 12 volts. If I subtract 12 more volts across this parallel split, I'm down to 0 volts. It adds up. Lastly, I can find the total resistance by going 36 divided by 9, and I get 4 ohms of electrical resistance for the whole circuit. Lastly, let's go ahead and figure out what our powers are. So do the top one, 36 times 9, and we get 324 watts of power. 12 times 6 is 72 watts of power. 12 times 3 is 36 watts of power. 24 times 6 is 144 watts of power. 24 times 3 is 72 watts of power. Now, most important part at the end of the problem, add these all up. Add up resistor powers 1 through 4. So 72 watts plus 36 watts plus 144 watts plus 72 watts. Indeed, all four of these add up to 324 watts. We know we did circuit puzzle number 7 correctly. Okay, on to circuit puzzle number 8. It's almost the same problem as number 7. The only difference is instead of a 2 parallel split, we have a 3 parallel split. So here's how it went. The total amount of black current splits into the blue and the gray. That total then splits up 3 ways, into the dark green, the light green, and the yellow. Those 3 then combine to the black, coming back to the battery again. The difference is this time we are given a battery voltage, okay, of 46 volts on the positive side, 0 volts on the negative side. We know nothing else about voltage, but we do know a lot of current, okay? Across R4 and R5, down at the bottom here, we know 3 amps of current goes across the blue pathway and 7 amps goes across the gray pathway. That must mean there are 10 total amps of current that come back together. It must mean that you started with 10 total amps of current to begin with. That means over here, you should have 10 total amps of current. So we can fill that out first. 10 total amps of current to begin with. Now that 10 total amps of current, ladies and gentlemen, is going to split 3 ways. Now it looks that 3 amps goes across the dark green pathway. Another 4 amps seems to be going across the middle light green pathway. How much is left over across the yellow pathway? Well, if 10 amps is coming into this 3-way split, then 10 amps must be coming out of it. So 3 plus 4 plus 3 adds up to 10 amps. So the remaining R3 current must be 3 amps. Now we can use a little bit of Ohm's law here to figure out the voltage across resistor 3. 3 amps times 6 ohms is 18 volts. So across resistor 3, down here, we know that there are 18 volts, volts of potential drop of 18 volts across the yellow resistor here, okay? But the yellow resistor is in parallel with both green resistors. And we know that voltage in parallel is the same. So if the yellow resistor has 18 volts of potential drop across it, that means the potential drop across the light green resistor is 18 and the dark green is also 18. So we can fill out voltage drops across resistor 1, 2, and 3. Okay, so we know a lot so far. So let's figure out some Ohm's law stuff here to fill this out. The total resistance would be 46 divided by 10, or 4.6. We know that 18 divided by 3 would give us 6 ohms across resistor 1. We know that 18 divided by 4 would be about, what, 4.5? Yes, 4.5. And so that fills out a lot. Now we get to this part here, okay? We know that the voltage drop across the total circuit is 46 volts. We know that the voltage drop across this chunk is the unknown. We don't know what it is yet. But we do know the voltage drop across this chunk right here, from this point to this point, is a total of 18 volts. Okay, so if we started with 46 and we subtract some number and then we subtract 18, we get down to 0. So to figure out this number here, subtract 18 from 46. So 18 minus 46, or 46 minus 18 is a total of 28 volts. Since there is 28 volts across the whole gap, and both of these are in parallel, that means there is a 28 volt 28 volts voltage drop across voltage drop of potential across resistor 4, and 28 volts of potential drop across resistor 5. Again, voltage in parallel is the same. All right, now we do a little Ohm's law calculation to figure out the resistors here. 28 divided by 3 is 9 1/3, and 28 divided by 7 is 4. Let's figure out our powers. Well, the total power would be 46 times 10, or 460. The power across resistor 1 would be 18 times 3, or 54. The power across R2 would be 18 times 4, which would be 72. Okay, the power across R3 would be 18 times 3, which is 54. The power across R4 would be 28 times 3, which would be 84. And the power across R5 would be 28 times 7, and 28 times 7 is 196. Now, let's add up all 5 of these individual powers. 54 plus 72 plus 54 plus 84 plus 196. Indeed, all 5 of these individual powers add up to a total of 460 watts of power. Again, these puzzles are a little bit more complex, but the same rules apply, okay? Current in series is the same. Voltage in parallel is the same. You are definitely using these 2 concepts to solve a lot, okay? The rest of it, you're using those 3 equations right there, okay? Have a great day.